let's begin. Again, welcome to our regular SMACCM talks. I will put any speculation to rest. Unfortunately, Brenton is not a candidate for the computer science position here.
It's news to me, too.
Unless you're interested. Brenton is a graduate from 2004, majored in computer science, and he went to work for Wolfram Corporation. Wolfram is famous for Mathematica. Along the way, he got a master's in computer science from IU. Okay, because you were actually in Bloomington, right? That's where IU is. Okay, and now he's actually working in Dayton at Marks and Labs, or actually Denver, Ohio.
Yeah.
And there was sort of a chance meeting between him and Brian Jackson, who discovered that Brenton was back in the area. So I'm just very pleased that one of our own has come back to Wittenberg to tell us what he's done in his life in computer science, and I made sure that all of my computer science students were here. Also, we have some of our emeritus professors here, Nancy Sachs and Jim. Oh, way in the back, yes. So we're just really pleased. I'm going to stop talking because I really want to hear what Brenton's going to say. So Brenton, take it away. You want to say anything, Brian, about the...
I think you said it all.
Take it away.
Thank you. So, like Dr. Shelburne was saying, I went to IU and I got my master's in computer science in 2009, I think. And I focused on the more theoretical computer science parts than more applied. And what I focused on the most, and what my thesis was on, was the idea of just proving when things can stop, when computations can halt. Not how efficient they are, not how fast or how little resources or anything they can take in optimal implementations, but just whether it's possible or not that they stop, which is a much more theoretical stance to take on things, but is a more foundational and important stance in my mind. One comes before the other. You have to prove something's even possible before you can make it better, I think. So today I'll be talking about just the idea of the border between finite processes and infinite processes, and how the border is pretty blurry to us, and we can't always tell what's what. Large numbers sometimes look like infinite numbers to us even, and we don't have a good way of telling, except through hard work, what's what. So, yeah, I think how the program even says astronomically large numbers, how to tell if computations ever stop, and how to add 1 to infinity. So I wanted to start off with the always great Saturday morning breakfast cereal comic. It's a very math science slant, and this is, George Cantor, as some of you may know. He'll come up a few times today, and as you can see, even as a young child, he spent a lot of time thinking about infinity and the concepts around infinity. So this is only in the last week it was published, so very serendipitous, I think. All right. So I think that the room's full of math and computer science type people, so they probably know about factorial functions. But the idea that you can take a function and then call it with a number that you don't know ahead of time is perfectly good. A well-founded idea, and does not actually change details of the function itself. Functions like factorial, quick sort, different things, they run in what we call big O terms. We can describe an algorithm like factorial or quick sort as big O of n or big O of n log n. And we talk about that in terms of the size of the input that we give it. But that's all independent of the actual input, obviously. So even if you don't know ahead of time what the input is to a function, you can still talk about what its behavior is. The fact that this factorial function terminates is true whether I plug in a 10, 100, or 1,000,003 into that function. So if you just imagine input as the function that accepts input from a keyboard and then you hit enter, any possible input, the input is independent of the function itself. So, but it is useful to be able to talk about how long something takes if we don't know what the input is ahead of time, when the input could potentially change how long the running time is in a way that's deeper than the simple recursion that's happening here. I know that sounds kind of spacey, but you could imagine that there are more complicated functions than factorial. There are, I can assure you, where the input changes the behavior of the function so dramatically that it doesn't make sense to use concepts like big O or any other kind of algorithmic analysis that goes on. You have to bring in deeper ideas to be able to talk intelligently about the function. But as you could probably have gathered, this function does terminate. I don't know where everyone is in terms of math and CS type classes and thinking, but it's easy to see that this always does terminate because any call to factorial is either the input that you gave it, which is just a single number, or it's some number that's less than the number that you gave. You can see just the n goes to the n minus 1, and the descent of n to n minus 1 has to eventually, no matter what it is, reach 0, and then you can see that that case is handled there. So no matter what input you give it, this function always terminates, and that's kind of a hand-wavy type proof, but that is what induction is. Recursive thinking, showing that eventually base cases are always reached, and there's no problem there. But you can start imagining more exotic functions.
Oh, yeah.
I don't know if that's a fan explaining
That'll bring any computer to its knees.
or an enemy. Already, this is slightly more complicated, and it's not as clear whether this function terminates or not. But in the same style of thinking, you can see that any call to, I see halfway through, Ackerman and A are supposed to be the same function. Those A's are the same function. Imagine that I'm changing that, fixing that right now. Any call is either with a call smaller in the first argument or a call smaller in the second argument. And then so in some hand-wavy sense, this function also always terminates. But we start getting into crazy territory where this function grows quicker, unimaginably quicker than factorial. To show you, just with the first argument of being 1, that's not so impressive. Adding 2 to a number isn't so impressive. But if you use 2 as the second argument, then that works out to be that function. And it's already ballooned, just with 3 as that first argument, it's already ballooned to an exponential. And what you can see is that if I just added 4 right now, it would be exponentials of exponentials exponentiating on itself. That's sometimes called tetration, in the same way, this progression of operations you'd have of, addition, multiplication, exponentiation, whatever that next thing is. That's simply calling that with 4 instead of 3. And so you could obviously call that with 100, and your mind starts reeling as to how big that number might be. I'm not going to write that out right now, but it's left as an exercise to the reader. to implement that. You'll get extra credit. But even though that's still big, this is still a finite number, and this still terminates, and there's still no problem whatsoever about proving that this terminates. They're very large numbers, and you have to be very, careful on everyday machines to even be coding this. But in theory, this is completely sound in the same way that factorial is sound. Now, so imagine this function. You're provided a greatest prime factor function just so that, if you, greatest prime factor of 14 would be 7, for example, and greatest prime factor of 12 would be 3. It's simply the single greatest prime factor of a number. Take that and subtract 1, but factorialize it, take out that greatest prime factor and multiply it by the number that you gave it. Does applying that function over and over again to any input terminate? As an example, that function 19, it's that number, which I will not read out, but you can see that it works. So this is actually original research on my part, trying to come up with a function that doesn't grow so fast as the next few will be, and that you can understand what's going on. I'll spoil it that it does terminate. This, no matter what number you give this loop always terminates, meaning applying this function over and over again always reaches 1, which may not make sense, but in an even more hand-wavy kind of proof, you can see that the factorial only ever applies to numbers less than the greatest prime factor of that number. And I also divide out that greatest prime factor. So each time I apply that function, you've taken out a bit, you've taken out that greatest prime factor. So in some sense, even though the number in absolute size might be ballooning to some huge number, if you just look at what each of its greatest prime factors are, you see that they always either stay the same for a while or they go down by 1. They never increase. And eventually, all of the prime factors will be divided out, and eventually you'll reach 1. Even though you have very, 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 very large numbers being generated at the start, eventually this reaches a peak, and then it eventually goes back down. But intuitively, it's very hard to see that understanding upon seeing it for the first time. Now, this is the function I wanted to make a better example of. This was originally discovered by someone named Reuben Goodstein, and he came up with a sequence, but I wanted to show it graphically. Imagine that you just had a tree of any size, depth, and arity. It doesn't have to be a binary tree. I know there are computer science people in here, so you have to be familiar with trees growing upwards. Pick any branch of that tree, and then add new branches at the root below it, multiplying out the remaining branch. You can see if I take out that third branch right now, applying that rule, multiply, add this branch 3 more times, corresponding to how many children there were. This is a complicated rule, but you can see that it would obviously lead to the tree growing very fast, very quickly. If I then took out one of these branches at the end, it would multiply even more, even faster, in a way that grows, that seems like it's just going to grow forever. But Goodstein proved that his sequences always terminate also. For example, I'm not going to supply his definition now, but I can supply references. But his function, given 4, takes this many steps to terminate, which is a large number indeed. So we get into this area where we might start thinking, just by using our intuition, almost everyone's thought upon seeing this for the first time is obviously the tree just grows and grows and grows. Obviously it grows forever, it can never stop. But that'd be wrong. In the previous function, the same way. Obviously you have factorial making something huge, so obviously it has to grow forever. But that would be incorrect also. So when dealing with infinity, it's hard to get everything right, and it often acts in opposition to your intuition. It does not matter what your intuition is about such things. You have to, it's like doing good science, basically. We're exploring this space for facts that are independent of what we think they should be at all. So does this loop eventually terminate? What do people think?
What was the negative input?
Well, this is always assuming positive, like 0 or positive numbers. Positive integers, the natural numbers. Those are the only ones that exist. Well, I was hoping somebody would be smart alecky and realize that on any practical machines that have 32 bits or 64 bits, yes, this would eventually terminate because of integer overflow. But that's not what I'm getting at. In a mathematical sense, does this ever terminate? And the answer would be no. This does not terminate, even though it looks like that obviously should have been a minus sign instead of a plus sign. So it's very easy to have bugs in any of your functions. Well, as we saw earlier, I swear, I meant to write out Ackerman earlier, but I was only writing out A's, so case in point. In implementations of functions, it's very easy to have typos, plus signs and minus signs. I don't know if anyone ever here has any trouble with balancing signs. I know I have. I never get signs right, But if that was a minus sign, eventually that would terminate after 100 steps. So we don't have a way of telling, we don't have a way of making sure what we're talking about is even what we actually need to be talking about. So we have not only reality fighting against our intuition, we have our own typos and keyboards fighting against us. So as computer science people, I'm assuming not everyone's code has always been perfect from the start, but I will at least say my code has never been perfect from the start. And there has been research into detecting how to stop such errors. Unfortunately, I don't even think that we have sophisticated tools enough to even detect this loop as being erroneous, but there has been a lot of research for slightly simpler loops to automatically detect. This is a screenshot from a popular Java tool, Eclipse, where you can write code. It knows that this is unreachable code after the while loop, and it probably wants me to remove it. Actually, I don't even think it lets me compile it. So this might be surprising for anyone who's ever heard of the halting problem in computer science. It looks like Eclipse has the halting problem built in, being solved, but Turing, almost 80 or so, 70 years or so ago, said that you couldn't solve the halting problem. So this might be confusing, but what he did was actually show that you can't solve it in general, for all programs, for all input, ever. This one example of a really, probably the stupidest while loop you could ever write, which is easily detected to be unreachable. So despite having this really depressing, negative result off this, yeah, please, ask any questions.
Can you tell me what the halting problem is?
Yeah, I mean, in a roundabout way, I'm motivating it.
Okay.
It is easy to write buggy code. I don't know if anyone's aware of that. It would be nice if we had a way of preventing writing buggy code, loops that run forever before actually running them and realizing that they're running forever. So even before computers existed, they existed in the mind of one man, Alan Turing basically, who was thinking very deep thoughts about the idea of computations. And he was wondering what was even possible in principle, in theory, for computers to do. Not how fast, not what the newest instruction set of the Intel i7 is going to allow, but just in theory, what is even possible. And on pieces of paper and in his own mind was able to realize that unfortunately debugging is always going to be hard. Debugging, you're always going to need to, there's never going to be any silver bullet, I should say. There's never going to be any shortcut to be able to hand your code to other code and have it say yes or no, this is good, always going to terminate code, or this is bad, it may loop forever on some inputs, code. That function does not exist, unfortunately, let alone having an efficient implementation. If it even existed, I don't even know how you begin implementing it. But in general, always with a caveat of being in general, because obviously, as we see here, you could just set up something looking for the literal characters, W-H-I-L-E, T-R-U-E. For this one case example, I can guarantee that's not how they implemented this in Eclipse, but there are simple cases that you can detect and still have the entirety of the problem ahead of you, because the halting problem is an example of a problem that's research that will always be inexhaustible. No matter how much work you've done for detecting, buggy code and loops, and so, there will always be one more attack or one more bug that could be in your code that will go undetected. But we don't, obviously we don't have an automated way of finding out what those one more attacks are. Otherwise, we'd always be able to, having a little progression going on. So there's no automated way to do anything effectively, which is sometimes depressing. Negative results can be a bad thing, but in another way, you could think of it as job security, because how sad would it be if you didn't have to write any more software and you could just have computers spit out the software from, I don't even know, 50, 60 years ago? That wouldn't be any fun at all. So, but this is XKCD and this is supposed to be funny, but I realize if I have to explain it, it's probably not that funny. But the big picture solution to the halting problem is to return true. In the heat death of the universe, yes, everything will halt. But that's never the sense that computer science means halting. Always in the mathematical, perfect, platonic sense of halting, no matter what, with really no ties to the physical universe if they can help it. So anyway, this is a screenshot. I don't know how good it can be read, but this is a scan from the Logic Comics comic book, graphic novel that was written by some computer scientists and mathematicians about the life of Bertrand Russell, who lived to almost be 100 years old and was involved with many of the advances of foundations of math and the beginnings of computer science. And so this is him visiting George Cantor in an insane asylum that Cantor was put into after thinking about infinity for too much. He really was committed. I don't know how factual these quotes are, but Turing used Cantor's ideas of diagonalization for enumerating real numbers and applied it to the halting problem to show that the halting problem is false. And this is what happens when you think about infinity too much. You get sent to an insane asylum. So not to put anyone off here from thinking about such things. But, so, I want to talk about assuming that you do have code that terminates, not that last bit, but the Ackermann function, factorial, the brief product factor function that I had in the Hydra game and the Goodstein sequences. Through some higher power, assuming that you have loops that always terminate, how you would go about proving concretely that they are proving, waving my hands, but obviously waving hands I don't think is an acceptable homework answer for math, for proofs. How would you go about proving it rigorously? And so George Cantor also provided the answer for that in the form of the ordinal numbers. And so, which he came upon by accident. He discovered them while working on a problem on trigonometric series that seemed like they're totally unrelated to the ordinal numbers. But what the ordinals are a way of concretely talking about processes and ideas that don't take an infinite amount of time, but take an unbounded amount of time, or an unbounded number of steps. And so you start off with the naturals, and there should be 0 in front of, 0 should be counted there. But then, in a sense, needing a way of speaking about not any one specific natural number, but making a choice among any of the natural numbers. And so the symbol used is omega, lowercase omega, to represent the idea of the set of all natural numbers when you make the choice. Basically, the input function from earlier is kind of like omega in the way that you're effectively just choosing from the set of natural numbers. What the interesting thing is, once you make that choice, you can go ahead and do more work with those choices. The idea of omega plus 1, omega plus 2, and so on makes sense. The idea of omega times 2 makes sense, and the idea of omega squared makes sense, and this makes sense, but I'm not saying it out loud. But the idea of building up, using omega as just another symbol like the naturals is well-founded. That's like fun. And can be manipulated much like the other natural numbers, but not exactly like the natural numbers. So the ordinals are useful because there's no infinitely descending series of them. No matter what ordinal you pick, perhaps to start off with in a process, let's say you assign omega squared to one of the earlier functions we were dealing with. That next step of the function would be assigned some other ordinal that would be strictly less than omega squared. And then the third step would be assigned yet another ordinal that'd be even less. And in that assigning process, you come up with a sequence of descending ordinals. And because the ordinals are well-founded, there is no infinitely descending series of ordinals. And you've basically proven that there are only a finite number of steps needed to show termination. And so, in a way, this is basically just casting the question of termination in a different light. These aren't really more powerful tools or any less powerful tools than simply asking about termination. This is just termination cast in a different light. So, any other questions so far? I know ordinals are kind of strange, but what you can do with them might seem counterintuitive. For instance, that omega plus 1 makes sense, but 1 plus omega is not the same thing. Addition is not commutative with the ordinals. And in that same sense, multiplication is not commutative with the ordinals either. And you can see why that would be if we think of, just talk about 1 plus omega. If we think about omega as the set of natural numbers and adding 1 to that set, we can start listing out the set of natural numbers like this and go on forever. We could ask about what adding 1 to that would, what that would be. So we could add up some new symbol that hasn't existed before. Go on. But if we just relabeled these symbols to be the same as what we had before, we'd see that 1 plus omega is actually the same set as the natural numbers. And that 1 plus omega actually equals omega. All right, you've always heard adding 1 to infinity, is infinity. So that's still true, but what about adding 1 to infinity, but the other way? If we think about it this way, what we have is first the set of natural numbers, and then we have this new symbol. And if we relabel all of these previous symbols, there comes this ellipsis. That's the this is the set of natural numbers. This doesn't affect that. There's still one more element that we weren't talking about before in a different sense than the finite number of elements that we were listing before this that could always be relabeled. Now, obviously, 1 isn't special, the same way 3 plus omega, is still omega. And so you can add 1 to infinity, but only if the 1 comes after. It matters because in the same way, you might want to always just write the 2 in front when you're multiplying, because omega you might be seeing it as a variable, so this would be the natural way of writing it, but in the same sense, this is the same thing as some sequence of 0, and then basically if you have 2 copies of omega of the natural numbers, you have some new second set of symbols, 0, 0 prime, 1, 1 prime, 2, 2 prime. The limit is never reached for either of them until the very end. So they could all simply be relabeled, 1, 2, 3, 4, 5, 6, 7. And so you can see, 2 omega is still omega. But omega times 2, which is different, is 2 copies of omega dot dot dot, and then 0 prime, 1 prime, 2 prime, 3 prime. And you can see that that's a different way of talking about the sequence than that. Like, these are not the same sequence. So this is a new entity. This is a new set that actually contains 2 different copies of the natural numbers. So ordinal arithmetic can be tricky, even though it looks like it might be just the naturals with, one more symbol added. But always being careful to talk about, the commutativity, making sure the symbols are the same, on the same side. So if something was to take, an omega number of steps, what would be some code that would look like that? Well, if you accepted some input from the keyboard, and while it's not 0, you decrement that number until it reaches 0, this terminates, and it takes omega number of steps. And that's the only intelligent way we have of talking about this, because we simply don't know anything more about this until we actually see the input. Obviously, if I change this to any hard-coded value, that would only take that many steps, or even 1,000,000, or even the large numbers that I had up later. Those would all be finite, but we have no way of knowing that ahead of time. In the same way that big O analysis doesn't take the actual numbers into account when they're talking about them. They only talk about the size of the inputs. So this is a similar way of reasoning. But as you can see, there are concepts like omega plus 1 and omega times 2 and omega squared that might not seem like make sense in code. But if we just nest these 2 loops, nest it with another loop, and basically just do the same thing, maybe making this look not completely pointless and printing out the number for fun. Minus. So on each iteration, for example, if I took a new input from the keyboard, each outer loop taking a new input for the inner loop, and then having to do that would take omega steps, but it would take omega many steps for each one of those steps. So in a sense, this takes omega squared many steps, even though it's quadratic and it's big O of n squared in some sense. If these inputs were more well known and more related, but this is an example of an omega squared algorithm, I'll say. And so omega to the omega power kind of doesn't even make sense now with for loops, because you would have to be iterating that many times. Instead of having only 2 loops, you'd have to have the number of loops determined by an input. And so you start getting into very mind-bending type situations. I don't know if everyone's still with me or not, but I appreciate the pretending that you are. You might think that just talking about omega would be the end of the ordinals, but you can ask what, in the same way that omega is the limit of the natural numbers, what would be, the limit of taking omega to the omega'th power many times? And normally that isn't well defined, but in the ordinals it is. And we've given it the label of epsilon naught. And this is an extraordinarily large doesn't even begin to describe how large this is, It's a concept that's so powerful that this is needed to prove the consistency of all of the mathematics that you work with in everyday life. That's what this number is, epsilon naught. PA for piano arithmetic. Gensen, a long time ago, roughly around the same time as Turing, proved that induction up to that number is the same thing as the consistency of piano arithmetic. So pretty powerful stuff. And he proved that that was needed. The consistency of arithmetic isn't independent of this ordinal or anything. You need induction up to that ordinal. And when we go with induction beyond omega, Cantor, yet again, didn't like talking about infinity because I guess he was a deeply religious man, as you can see, and was bothered by just the names of infinity. So he came up with talking about the transfinite numbers, the transfinite ordinals, and induction like this is called transfinite induction. Nowadays, I don't think we care so much about blurring the lines between finite and infinite, thinking that we need a third thing that's in between. I think we would be okay with, calling this something like infinite induction, but it's just called transfinite induction, which, if anything else, I think that's just a cool name to repeat, even though it's not really needed anymore. So if you thought that was a large number, they just get larger. There's the idea of gamma naught, named after these two guys, Pfefferman and Schutt. You might think that exponentiation isn't that special, like I was talking about before with acronym. You could just make it tetration, and there could be many more operations, so epsilon naught isn't really that special. If you could think of other ways of building up operations, and all of those, and there are clever ways of building up operations, let me tell you. There's a way of representing the ordinal that contains all of those, and that's called gamma naught. Makes epsilon naught look like, epsilon. But these are just names for things. There's also omega 1, I never really know, omega 1 super CK, I don't even really know how to pronounce that. But the idea of gamma naught might be cool and all, but we can still write it down. We can still, we can still talk about it just fine. So that's not really that cool. What we should make even bigger is talking about the idea of the ordinal that contains all possible computations, which is a tad larger than gamma naught. The idea of containing all computations ever, forever, ever. That's in this idea of the omega 1 CK, named after Church and Clean. Yeah. two very foundational members of the Math and Computer Science Society, obviously. And after this, it gets tricky because you don't really have notations for what you're even talking about and ways of working with them. But you can only give definitions. And so what you just then do is, you just talk about the smallest, we don't even want to talk about, notations or definitions or anything. Let's just talk about things that we can't even count anymore. And they give such a tiny label to an omega 1, but it makes it seem like it's like any of those other ones. And it's almost a historical fluke that they share it with CK, even as unrelated as they might be. But that's pretty much the largest ordinal you could be thinking of, even though it is not the largest ordinal that exists, because, believe it or not, there is no largest ordinal. Because if there was a largest ordinal, you'd be able to add 1 to it, and that would be another ordinal. So people quickly realized that the same way that all these set theory paradoxes came about and needed well-founded, there's no actual largest ordinal. But you can talk about them getting pretty big, though. So those are unbelievably big. But even after talking about the ordinals, there's no way there's no prescription that we have for assigning ordinals to processes that we have. It takes very clever mathematicians to come up with them, and that's their, as their day job. There's no automated way of doing that. And so I was asking before if certain loops were terminating, and they were kind of trick questions. Yes, they were always terminating up until the last one that wasn't terminating. But so this is a problem in number theory that currently exists. Given this function on the naturals, which is pretty easy, 0 for the first time is actually excluded from this, starting at 1. Applying the function over and over again, does this process terminate? And the answer is that we don't know yet, right now. As simple as this is, we don't have the machinery to talk about how to assign ordinals to this process in a way that shows that it terminates. If any one of you is clever enough to come up with a way of showing that, you'd be very, very, very famous, and would probably be able to, it's not actually one of the $1 million questions from the Clay Institute, unfortunately, though. I believe that it should be one of the $1 million math problems. But you can see that it kind of starts off, if you just picked 5, for example, you'd get 16, and then 8, and then 4, 2, and then 1. And then you reach 4, 2, 1, and it stays in that loop. But if you start at 7, it goes 7, 22, 11, 34, 17, 52, 26, 13, 40, 20, 10, 5, and then does the same path as before. So everything I've shown you before was either going straight down or growing up once and then coming back down. The Hydra gain in my prime factor example. This is an example of a very simple function that grows. It almost looks like white noise. It's very strange. And so as much technology and machinery that we've built up over the years of understanding infinity and proving termination and things, we don't have all the answers just yet. So, and that's inspiring to me. And so I'll close with a screenshot from another page in the Logic Comics comic book. This is Russell going to go visit Cantor. He was talking about how I was going through and I noticed that Wittenberg in Germany, I guess, had just been incorporated into another university. And so I thought that was very appropriate to include that for this talk. As he's talking about Wittenberg as he's going on to go visit Cantor in the insane asylum. So I thought that was nice. So that's that. I think that was a whirlwind. Does anyone have any questions?
Yeah, go back to the colors, which, by the way, I recall when you were here, you were actually interested in that problem.
I haven't quite solved it yet.
Yeah. So what you were looking at is basically looking at functions and trying to find out if they terminate or not. That's a very simple function, which nobody knows if it terminates. We suspect it does. We don't know.
All right, I should say all evidence suggests that it does.
Yes.
That doesn't, that's not a proof for all, but right, you'll find that any example that you try, it does terminate. But as we were talking about, that's not the same thing as providing a proof of termination. Very interesting. And in the same way that the Goldbach conjecture is related, every case we've ever examined has always shown that the Goldbach conjecture is true, but if you have a proof for that, you shouldn't sit on it either. You should publish that also. That would be another very important result if you came up with that. But it's a similar kind of thing. Easily stated questions don't necessarily mean easily stated answers.
The thing about the Goldbach conjecture is some thought that maybe it is true, it can't be proved.
Right. And so that gets into, what kind of proof system you're even working in and how powerful the system is. And if it's something that's not provable beyond arithmetic, then it's not hopeless, but it's going to be beyond the realm of many mathematicians and people thinking about the problem. And there have been examples of it. The Hydra game that I was showing you, requires it. But it would be unfortunate, but it would be so interesting if it did though. Any other questions?
How about some interesting applied computer science problems?
To this?
Yeah, this, some you've seen.
Well,
You've been with Wolfram, you're with a couple other companies. Your answers, what kind of interesting applied computer science problems, some of the group here tonight.
let me go back. So this is the work that goes into detecting this type of code and warning you about it. Will always have to be done, like I was saying before, it's job security, but it's unbelievably interesting because it's constantly, you should never underestimate the intelligence, you should never overestimate the intelligence of people and how likely it would be that they will find a way to break your tools and come up with a new way of, having their code, be buggy, as much as you might examine it. And so, what we've seen, like I've worked in the industry for 10 years or so, from Wolfram to where I'm at Marks & Labs now. I program in Java every day, and Eclipse is the biggest tool for that. And this is a screenshot from that, like I was saying. The technology that people build into IDEs, the same thing with Visual Studio though, and Xcode, and any other IDE you can think of, is so advanced nowadays. It helps you with auto-completion of function names, and will tell you when you're calling a function with the wrong kinds of arguments and things. But there's been so little comparative work to finding bugs like this in code because it is so unbelievably hard. Microsoft Research is dumping millions of dollars into this type of research, though. Byron Cook at Microsoft Research leads a group currently building tools called the Terminator for helping detect problems in code like this. This is very simple. You might imagine when your code starts spanning hundreds of pages that it's not as simple to figure out anymore. And so it's many people's full-time jobs and interns and research assistants and everyone. When I was at Indiana, I was researching termination and doing this kind of thing. just trying to help out and make everyone's code better. So it's definitely a hot, making code better is almost the hottest part of computer applied theory, if I can say that, in computer science. So.
Any other questions? Well, let's hear from the speaker.